At the center of our solar system blazes a star that has shaped everything we know, the Sun. It gives us warmth, light, and life itself. Every heartbeat, every breath, every green leaf that turns toward the sky owes its existence to the ceaseless energy of this ancient, burning sphere. But the Sun is not simply a ball of fire. It is a vast, living machine, a fusion furnace of unimaginable scale where matter and energy dance in intricate, violent harmony. For centuries, it seemed we understood it well. The deeper you go toward the Sun's core, the hotter it gets. The farther out you move, the cooler it becomes. That, we thought, was the natural order of things. And then we looked closer. What scientists found defied intuition, defied logic, and challenged the very foundations of astrophysics. For above the Sun's visible surface, beyond the photosphere, where temperatures hover around 5,500 degrees Celsius, lies a region so hot it almost seems impossible. The corona, the Sun's outer atmosphere, reaches millions of degrees. How can the outermost layer be hundreds of times hotter than the surface below it? This is the great solar paradox, the mystery of the superheated corona. To understand this mystery, we must first journey through the Sun's structure, layer by layer. At its core, nuclear fusion converts hydrogen into helium, releasing immense energy. The very heartbeat of the Sun, temperatures there reach 15 million degrees Celsius. This energy radiates outward through the radiative zone, where photons are absorbed and re-emitted countless times, taking thousands of years to escape. Next comes the convective zone, a turbulent ocean of plasma currents. Hot material rises, cools, and sinks again, driving the Sun's boiling, ever-changing surface. Above that lies the photosphere, the layer we see with our eyes, golden, radiant, but relatively cool at just a few thousand degrees. And beyond it, the chromosphere, and finally, the corona, a ghostly halo of plasma that extends millions of kilometers into space, visible only during a total solar eclipse. But here's where the mystery deepens. Instead of cooling as it extends away from the fusion engine, the temperature jumps dramatically. The photosphere is about 5,500 degrees Celsius. The corona can exceed 2 million degrees. Somehow, energy travels outward, skips the intermediate layers, and deposits itself into the Sun's outermost atmosphere, heating it to astonishing extremes. When scientists first detected these coronal temperatures in the 1940s through spectroscopy, they were stunned. The data suggested that ions in the corona moved at incredible speeds, far faster than could be explained by simple radiative heating from below. It was as if heat were flowing backward, from the cooler surface to the hotter outer layers, a violation of everything thermodynamics teaches us. And so began one of modern astronomy's most enduring mysteries. For decades, physicists have searched for an answer. What mechanism could possibly heat the Sun's corona to such extreme temperatures? Several theories emerged, each elegant, each incomplete. The first looked to waves. The Sun's surface constantly trembles with sound-like vibrations called acoustic waves, generated by the turbulent convection below. These waves could, in theory, carry energy upward. But calculations soon showed they lacked the power to heat the corona to the observed millions of degrees. Then came magnetohydrodynamic waves, or Alfvén waves. Oscillations traveling along the Sun's magnetic field lines, like ripples running down a taut string. These waves could transfer energy efficiently from the lower atmosphere into the corona. But how was that energy transformed into heat? What caused it to dissipate? A second theory looked instead to magnetic reconnection, a violent process in which tangled magnetic field lines snap and rejoin, releasing bursts of energy. These reconnections could happen on both massive and microscopic scales, creating a steady drizzle of energy, nanoflares, across the solar surface. Individually, each is tiny. Collectively, they might account for the corona's fierce heat. Today, most solar physicists believe the answer lies not in one process, but in both. A symphony of magnetic activity and wave-driven heating combining to pump energy into the outer atmosphere. To truly grasp this mystery, we must see the sun not as a static sphere, but as a churning magnetic engine. Beneath its surface, vast rivers of plasma twist and churn, generating magnetic fields that rise through the photosphere in loops and arcs. These magnetic structures pierce the surface like invisible threads, arching into the corona and binding it into intricate patterns of light and motion. Where magnetic field lines intersect, tension builds. When they snap, energy is unleashed, sometimes as solar flares, sometimes as coronal mass ejections, and often in countless smaller events invisible to the human eye. Each reconnection releases enormous bursts of energy, accelerating particles and heating surrounding plasma. Over time, these micro-explosions could collectively keep the corona at its staggering temperature. In this view, the corona is not heated passively from below. It is electrified from within by the sun's own magnetic heartbeat. For centuries, the corona could only be glimpsed during total solar eclipses, fleeting minutes when the moon perfectly covers the sun's disk, revealing the ethereal white halo that encircles it. But modern instruments, like coronagraphs, block the sun's glare, allowing continuous study of this enigmatic region. Spectrometers and satellites have revealed coronal loops, towering arcs of plasma following magnetic field lines, and coronal holes, dark regions where magnetic fields open into space, letting solar wind escape. Each observation adds a new piece to the puzzle, painting a picture of dynamic, explosive beauty. Yet, the complete explanation of the corona's heat remains elusive, one of astronomy's most tantalizing frontiers. In the early 21st century, humanity took a bold step closer to the source. NASA's Parker Solar Probe, launched in 2018, became the first spacecraft to fly through the sun's corona. Protected by a revolutionary carbon composite heat shield, Parker is gathering data from a region once thought unreachable, measuring magnetic fields, particle flows, and the very waves that may power the corona's heat. Its observations have already revealed stunning results. Magnetic switchbacks, reversals in the solar wind's direction, bursts of high-energy particles, and unexpected fluctuations in temperature and density. Each new orbit brings Parker closer to solving the mystery that has puzzled generations. Meanwhile, the European Space Agency's Solar Orbiter complements Parker's mission with high-resolution imagery, mapping the sun's magnetic surface in unprecedented detail. Together, these missions are transforming our understanding of how energy moves through the sun and, by extension, how it shapes the environment of every planet in its orbit, including Earth. The sun's corona is not an isolated phenomenon. It is the source of the solar wind, a stream of charged particles that flows outward through the solar system, shaping planetary magnetospheres and space weather. When this wind collides with Earth's magnetic field, it creates auroras, disrupts satellites, and stirs the upper atmosphere. The heat of the corona drives this constant outflow of energy, connecting the sun to every world it touches. Thus, To understand the corona is to understand the cosmic heartbeat that governs our space environment, the engine of light and motion that sustains and challenges life on Earth. The mystery of the sun's corona is more than a scientific question. It is a philosophical one. It challenges our assumptions about how nature works, reminding us that even the most familiar star can still defy expectation. We once believed that heat and light flowed outward in a simple gradient, that the universe obeyed the neat symmetry of our equations. Yet the corona reveals that the cosmos is subtler, more intricate, and more alive than we imagine. In every filament of plasma, in every magnetic ripple, the sun tells a story of turbulence and order, of chaos and balance, of energy finding pathways we have yet to fully comprehend. The mystery endures, but with each discovery, we move closer to understanding how the sun, our oldest companion, still surprises us after billions of years.